Alright, let's look at the Navier-Stokes equation. In particular, we would like to start with the continuity equation. Alright, now consider a container. We'd like to study the mass of liquid going into this container and compare with what is going out. So mass in and mass out. The conservation of mass requires that the mass in should be the mass coming out. And in this regard, you can say the change in mass into the container is almost the change in mass outside the container. And you can call this equation 1. We already know that if this, because we're looking at fluids, right, or fluid-like substances, you definitely would be looking at the volume of the container. So to take the volume of the container into account, you can say that density is mass over volume. Density is mass over volume, and you can now say mass is density times volume. And this gives you the opportunity to rewrite equation 1. So d by dt of rho v. In this case, v is the volume, or perhaps we can say that dm is rho dv. So that we are looking at the mass of a tiny section of the fluid flowing into through the container, and so that the mass, the total mass in, for example, would be the integral of rho dv across the volume. Then you can write this as integral of rho dv. You can put d by dt here, or you can put it inside, depending on how you want it. So d rho by dt dv equals the one that is going out. We can look at, okay, so let's first put it in. Let's write it in this. So don't forget, this is in, then you will have rho out, and then dv, right? Now it turns out that you can write this mass coming out in terms of the area, multiplying the length. So this is the area, for example, multiplying the length. But how many areas have we? We also have this area, and I wish I can draw properly, and maybe I can do something, and that area, an area of all faces. So in this case, you can rewrite the right hand side. So the left hand side remains integral of d by dt rho dv equals, you can rewrite this like this. Rho out times L, sorry, there is this, right? So d by dt of rho times dl, that is the length, say a small length in this direction or in this direction or in whatever direction. But whatever direction you are taking, there is an area facing in the normal direction. So if you're looking at this, the n is like this. If you're looking at that, the n is like that. If you're looking at the area beneath, there is an n. So in general, you can say dl dot n times the surface area. If you are looking at the surface area, it has to now be closed. So the reason for this ring is we are looking at all surface area across the cube. So this surface area, also this surface area, also this surface area, and all other surface areas. And that's the reason why we have this ring. This ring is trying to tell you it's a counter, like it's all over the surface area. And now we can say that because we already know that, so you have length, and therefore you will now need a second integral for the length, which if you integrate will eventually become L. And you can say but dl by dt is velocity change in length, so you can call it v, and this becomes d by dt of rho dv equals counter integral of rho v, that's velocity, that's this L and this L and this d, so dl dt, and you now dot n ds, and finally you can let j, this is called current. It's going to be very important in the future for us. Current, let j equals rho v. Rho, that's the density times the velocity with which the fluid is moving across. And you now have integral d rho by dt dv equals counter integral of j dot n ds. Now we apply the divergence theorem to this. You already know the divergence theorem, so this one can be represented like this integral. Now instead of area we make it volume, but we have to take the divergence of j dv, and that's d rho by dt dv. And with this you can now say d rho by dt minus the divergence of j, because they share the same integral nature. You can say this is equals to 0, and then you can say but you cannot integrate over a volume to get 0 unless, so this is not equals to 0 unless what is inside is 0. So you can now say d rho by dt minus j is 0. This is called the continuity equation. And it will be really important in what we will discuss soon. What do I do here? Now that we have the continuity equation, sorry, I know you don't like it, but let's split these guys into. Now the fact that we have d rho by dt minus, is it negative or positive? Yeah, it's negative. Minus the divergence of j equals 0, where j is rho v. So that means you can rewrite this as, so you can say that the divergence of j is like saying the divergence of rho v, which is the normal product rule. You can say this is this times v, let's call it, plus rho times this, and you can put this back in here. You can put all of this, you can put them back in here if you wish, in fact depending on the condition. So because we're gearing towards Navier-Stokes equation for compressible fluids, you have to have this equation as it is. But for incompressible fluids, density is constant. Density does not change within the flow, and therefore you can now say that density change per unit time and density change per unit space, or you can say they are all not important. So for incompressible fluids, the fluids you cannot compress, usually these fluids are called Newtonian fluids, like water. Water is incompressible, okay, even though it to some degree compressible, but anyways it's approximated as an incompressible fluid. But what are compressible fluids? They are like gases, like oxygen, like methane gas, like the air we have around us. These are compressible fluids. So this is for compressible, and for incompressible this equation becomes only this term. That's the only thing that will survive. So d by dt of rho minus the divergence of j equals to 0. This guy goes to 0, and I already told you that this side will vanish because density does not change with space, and you end up with minus rho. So the only thing you have is this. So minus rho, the divergence of v equals 0, and you can ignore this guy, and that is very important for incompressible flow. we will use this in the Navier-Stokes equation we're going to be working with. Now, that's all regarding continuity equation. So to recap, continuity equation is like this: d rho by dt minus the divergence of j equals to 0, and this is the general continuity equation. Some they call it transport equation. And for incompressible flow, this becomes only this. That's all. Now let's move on to derive the Navier-Stokes equation. For the Navier-Stokes equation, we are going to begin with the momentum of the law of change in momentum. So Newton's second law. It says that sum of forces acting on the fluid are the reason why the momentum of the fluid will change over time. This is very crucial, right? So when the fluid changes, any change in momentum of the fluid is a consequence of sum of forces acting on the fluid. There are two types of forces. So this F has, there are two types of forces on the fluid. There are the body forces, I will call it FB. e.g. gravity, electric field, magnetic field. What do we mean by body forces? These are the forces that can influence all the molecules at once. Magnetic field can do that, electric field can do that, gravity can do that. And there is the second category of forces that can affect some part of the fluid, especially the surface. We call them surface forces. So these are e.g. stress. The stress across the surfaces of the fluid, and pressure, because the fluid is going through this way, so the pressure will be here, and then we push it. These are surface. So we can now rewrite. We can say, okay, dp dt, change in momentum of the fluid, can be approximated. This is an approximation. FB plus Fs. Now, for a unit mass of the liquid, you can say, you can go the same way we did. For a unit mass, we can say d by dt of mv, because momentum obviously is mass times velocity, equals FB plus Fs. For a unit mass, FB will become rho FB. Fs will remain Fs, because it's this guy. It's really important for us to clarify. This guy is acting on the surface. This guy is acting on the body, or you can say in the volume. This is the real momentum you're measuring. Now, that is for a unit mass. Now, to get the total mass or the mean mass, you can integrate across the volume and the surfaces, because it's just like it's just like you're now looking at all the surfaces and the volume itself. and in this regard you're going to integrate here. So m is the total mass, it's integral of rho dv, and we integrate this guy across the volume, this guy across the surface, this guy across the volume. That's what we're going to be implementing. And we can now say d by dt. So we're integrating rho v, how do I write this, rho v dv, integrating through over volume, and we're integrating this as well, rho fb dv, and we are integrating this guy over an area. If you can remember the way we managed here, so we are going to integrate over an area, so it's going to be fs dot n, this is a vector, ds across all surfaces. That's what we're going to be doing now. Exactly the way we did in the other time, we are going to apply divergence theorem. And you end up with d by dt of rho v dv equals integral of rho fb dv plus integral of, now the divergence, we need now the divergence of fs dv. And similarly, you can take the integrals off the way we did it here. You can say we cannot integrate over a volume and get 0 unless what is inside is 0, and therefore these guys will be free from the integration. You get something like d by dt of rho v equals rho fb and the divergence of fs. And that is this is called the Cauchy momentum equation, this one. There is a mistake I made. This fb does not have rho because it's a standalone force, so rho does not follow, sorry. Yeah, so it's a standalone force. This is the Cauchy momentum equation. That's the Cauchy momentum equation. Now, depending on what you want to do with this equation, let's copy the equation. You can define it, or you can redefine the forces. Let's go here, paste it. Now, if we consider a fluid like water, so for incompressible fluid, okay, first we would like to have the general form. It's really good. Let the body force be gravity. So that's Fg, which is rho g. Now we can put back the rho here. And the external force, let's assume we have only two forces. So Fs, let it be pressure. Let it be pressure. So pressure in the surface. So when we say pressure, we mean pressure in one of the, maybe in this way, or pressure across the surface, and the stress across the surface. So I'm using IJ because I'm looking at 2D. You can look at 3D, but to ease the, so we can call this pressure forces, and we can call this stress forces, or you can call it stress tensor. And now we rewrite this equation. So d by dt of rho v equals rho g and minus the divergence, so this one will become minus the divergence of P, or the gradient of P, sorry, pressure gradients, because pressure is, then plus the divergence of the stress tensor, or we can call it the gradient of the stress tensor. Anyways, so this is the Cauchy momentum equation for, in general case, for compressible and incompressible. This is IJ. It's just the same equation. It's just the same Cauchy momentum equation. But this time we have defined the external forces explicitly. We move along with this, and we now, there is this I did not explain. This is called identity matrix. The reason why it's there, because this guy is a tensor, and tensors are matrices, and therefore this is an identity matrix. But now I get rid of it here, assuming we are going to have, when we take the gradient, we're going to have equal dimensions. Now let's talk about this stress tensor. Sigma ij is defined in terms of the dynamic viscosity mu, dvi by dxj plus dvj by dxi, and the body or the bulk volume viscosity lambda. So this is called the dynamic viscosity. This is the bulk viscosity, or the volume viscosity, or they call it second viscosity. Anyways, it's also a viscosity term. Bulk viscosity. Kronecker delta Ij, we know what this guy does, and the divergence of V. Sorry, I'm changing the colors, but anyways, this is Kronecker delta. We know what it does. It is 1 when I equals j, and it's 0 otherwise. Now, this equation, the Cauchy momentum equation, is general, but it's for any fluid, gases and liquids. But if you're focusing on Newtonian fluids or incompressible liquids, then you have to apply this law. Where is this law? You have to apply this equation, and when you apply it, you come to realize that this term will have to go, this term, and you end up with sigma ij. Let's write it here. Sigma ij equals mu dvi by dxj plus dvj by dxi. And the fact that we need to take the gradient here, we can apply it before we substitute back into the equation. So the gradient of sigma ij would be mu d by dxi of all of this let's say d by dx, d by dy. Let's say the I is for the x and the j is for the y, and plus mu d by dxj of the same. And what will happen is that this is d by dxi. When it meets this one, you have, let's quickly do it, this mu, you have squared vi by, I can swap them. I can put this guy out and put this guy in. I can do dxj then dxi. I can do that. You can switch them. Plus mu d by d. So now this is xi, so you can say d squared vj by dxi plus mu, this one you can say d squared vi by dxj, and then you can say plus, we can also switch here and say d by dxi dxj of vj. And if you look at this one, because we have dxi of vi is like taking the divergence of v. So the divergence of v, naturally, if you do divergence of v, it's d by dx of vx plus d by dy of vy plus d by dz, for example, of vz, and that is d by di of vi. So it's like saying, so what I just wrote here is like saying d by dxi of vi, and this is 0 according to the principle, because we already have seen that the divergence of v is 0. This is 0, and therefore this term and this term would go to 0, because of this. And then you have this ij becomes mu, so you can factor, because you have this and that, you can call it this. Yeah, you can just call it this. And now we are in a position to substitute this here. For the compressive, so you can now say that for a compressible fluid, let's take this guy, or we can take only this guy. Let's take the plus, and then we put it here, and therefore now you can say paste. We can now say that this is plus mu L squared V, and that is the Navier-Stokes equation. This is Navier-Stokes equation. For incompressible fluid. If the fluid is compressible, you already seen the compromises we made. So in general, let's recap. We started with the continuity equation. We saw that mass going in equals the mass going out. We did what we did. We got the continuity equation. We did some analysis when the fluid is incompressible. So the continuity equation we got here is for the compressible fluid, and we switched on to Newton's second law, where we said that the total forces acting on the fluid is the reason why the fluid is going to have a change in momentum, and we express the change in momentum for a unit mass here. We integrate for the whole mass, and we realize we have two categories of forces: the body forces and the surface forces. And the body forces are those forces that act on the volume as a whole, like the forces that would act on each molecule individually. If you were to consider individual molecules, it will act. And the surface forces, those that are affecting the flow, but they are mainly pushing from the surfaces. And we are able to apply the divergence theorem to get the Cauchy momentum equation, which we then defined the types of forces, and we made some compromises, and we ended up with the Navier-Stokes equation. Now the Navier-Stokes equation as well, in fact, we already have known that this is one of the most difficult equations to solve analytically, and there are ways around it, one of which is what we're doing in this course, the numerical method. But for analytical solution, we might reduce this, so we might make some assumptions. First, let's make it 1D. Second, let's make it incompressible. Already is incompressible, so it's fine. Let's involve the assumption incompressible. So anytime you mention this name incompressibility, you have to call this equation to help you. Anytime you make this assumption, you have to. And then third, we would like to assume the gravity effects rho g and the pressure effects, let's assume these are negligible. And this equation will now become something like this. It's 1D, so 1D, let's take only x component of u. So you're going to end up with an equation like this. dv by dt, rho is here, equals, this guy is 0, this guy is 0, so you have mu or sorry, we're in 1D, so we can say d squared v by dx squared. And that's there's something we did not touch on, which I would like now to introduce. This, according to normal calculus, v would be v, because this equation means that v is a function of x and t. And according to calculus, if you want, because this is called total derivative. Total derivative is when you say dv, that means you are looking at the change in v with respect to time, dt, plus the change in v with respect to x. This is standard calculus. But we didn't have dv. What we have instead is dv by dt. So when you do dv by dt, becomes like chain rule. So this would be by dt, and this would be by dt. And you end up with dv by dt becoming dv by dt plus dx by dt is v. dv by dt is like, so you're like taking the gradient of v and multiplying by v. Yeah, because this is like saying grad v, and this is the v itself, and therefore you have something like that. And it's usually represented this way. We bring this b v, it's because a dot b is b dot a, and therefore you can switch them. You can call this v dot grad v. Anyways, we put this back in there, and we have let's divide here by rho and here by rho, so that this guy goes. So you have dv by dt plus v dot, or you can say plus v dv dx. Yeah, dv by dx, you can say that, because the gradient, let's call it, because it's in 1D, equals gamma d squared v by dx squared. Let's do something like that. D squared v by dx squared. This is called Burger's equation. This is called Burger's because it has solution. And what is this gamma? It's just a name for mu over rho. So gamma is the dynamic viscosity over density. We call it kinematic viscosity. And that's the Burger's equation. So we can call it 1D viscous Burger's equation. So we can call it 1D viscous. There is U here. Burger's equation. This is a prototype nonlinear advection diffuser, because this term here, V dv by dx term, is advection, and gamma d squared v by dx squared is diffusion. So this represents advection, this represents diffusion. What do we mean by advection? Flow. That's all. Flow is just like flowing. It represents the flow with some given velocity, v. And the diffusion, so advection is flow and diffusion is also flow. What is the difference? This is artificial flow, and this is natural flow. This one has direction, this one is chaotic. Diffusion can spread, it's just spreading. So advection can go like this, but diffusion can, and that is that's the Burger's equation. It has analytical solution. Thank you very much for listening.